continue to the next question. Question 1.3. An object is dropped from two different heights, height for h and h, above the ground. When dropped from a height for h above the ground, the object takes t seconds to reach the ground. The time that the object takes when dropped from height h is, so let's write the equation. Delta y is equal to v t plus half acceleration t squared. Acceleration is g here. So this is equal to half g t squared, which is our t is the time it takes to reach the ground when dropped from 4h. So now we want the time it takes when dropped from h. Note that displacement is directly proportional to the square of time. So then from 4h to h, we reduce this by a quarter. So 4h to h is reduced by a quarter. Then that means that the time will also be reduced by quarter, but to the power 2, since it is directly proportional to the square of t. So the time then is going to be reduced by 1 over 16t. So the correct answer there is A. Question 1.5. A ball is dropped from rest and reaches velocity v after it has traveled 3 meters. What will the magnitude of the velocity of the ball be after it has traveled 9 meters? Ignore the effects of friction. And here the equation that relates velocity and displacement is v final squared is v initial squared plus 2g delta y. It's dropped, so we deduce that the initial velocity is 0. So the final velocity is the square root of 2g times delta y. Then we observe that the velocity is directly proportional to the square root of displacement. So when you change the displacement from 3 to 9, you are changing it by the factor of 3. So the displacement y prime is equal to 3 times y. So this means that your new velocity is going to be, so v is directly proportional to the square root. So new velocity is going to be the square root of 3 times the old velocity. So the answer there is B. Question 1.5. If the momentum of an object is doubled, then the kinetic energy of the object is, so here we'll just write the equation that you're probably familiar with if you went through the videos on math skills, proportionality. Kinetic energy is momentum squared divided by 2 times mass, which means that kinetic energy is directly proportional to the square of momentum. So then if you double the momentum, then that means that your kinetic energy is going to be 2 squared the original kinetic energy. It's proportional to the square, which is k prime is 4k. So then the answer is number D. Then question 1.5. Kinetic energy of a car moving at constant velocity of 2v is k. Velocity of the car then changes to a constant velocity of 4v. Which one of the following represents the kinetic energy of the car at a constant velocity of 4v? This one should be trivial. Know that kinetic energy is directly proportional to the square of velocity. So then if we change the velocity And the new velocity is twice the original velocity, so 2v to 4v. It's multiplying by 2, then let's square there. Then the new kinetic energy is going to be 2 squared the original kinetic energy, so that's going to be 4k. So answer there is C. And then the kinetic energy of a moving object can be quadrupled by, quadrupled means increasing it 4 times. So you can achieve this by, from this equation, half mv squared. We know that kinetic energy is directly proportional to the mass, and kinetic energy is directly proportional to the square of the velocity. So if you increase the kinetic energy 4 times, then doubling the mass is not going to do. So that won't do. Doubling the object speed, that will do. And obviously C and D are wrong. So the correct answer there is B. Question 1.7. 3-point charges Q1, Q2, and Q3 are fixed in a straight line. Q1 is r meters from Q2, while Q3 is 2r meters from Q2, as shown in the diagram below. The magnitude of the charge on Q2 is Q. Net electrostatic force on charge Q1 is 0. What is the magnitude of charge Q3 in terms of Q? So let us first note the information that we're given. We're given that the distance r from charge Q2 to Q1, 2 to Q1 is r, and the distance from charge Q3 to Q1 is 2r plus r, 2r plus r, which gives us 3r. If the magnitude of charge Q2 and magnitude of charge of Q3, if they were the same, then the force that Q3 exerts on Q1 would be 9 times smaller than the force that Q2 exerts on Q1, because force is inversely proportional to the square of the distance. So then, since such is not the case, we're given that the force Q3 exerts on Q1 is equal to, but in an opposite direction to, the force that Q2 exerts on Q1, so that the net force on Q1 is 0. So we conclude that the charge, to compensate for the fact that QR is 3R away from Q1, which would make the force 9 times smaller, so then the charge Q3 must be 9 times greater than the charge of Q2 in order for these forces to be equal. So therefore the answer is D. Let's look at another 1.7. We have two identically charged spheres, X and Y, carry charges plus 2q and minus 6q respectively. Sphere X experiences an electrostatic force F to the right when the distance between their centers is r. So then the spheres are brought into contact and are then returned to their original positions. Which one of the following represents the magnitude of the electrostatic force that sphere X experiences now? So let's respond to this. Coulomb's law, from Coulomb's law, that the force is directly proportional to the product of charges, magnitude of these charges, product of the magnitude of the charges, and is inversely proportional to the square of the distance between the charges. So since the distance has not changed, what we need to determine is whether the magnitude of the charges have changed, and if so, to what value. So in order to do that, we will invoke the conservation of charge formula. Q nu is equal to Qx plus qy divided by 2, which is plus 2q plus minus 6q divided by 2, and that gives us minus 2q. So then, as the magnitude of charge on sphere X changed, so from plus 2q to minus 2q, the magnitude has not changed. So magnitude of the charge on sphere X has not changed. By magnitude, I mean the size. So whether this is plus 2 or minus 2, the size is 2. And what about the magnitude on sphere Y? It has changed. So the magnitude here is 6q, and now the new charge is 2q. So then the qy, new charge on qy, is a third of the original charge y. So from 6 to 2, you multiply by 1 over 3, and from this formula here, force is directly proportional to the product of magnitude of the charges. So then if I reduce this charge by a third, then the force will reduce by a third. So the answer here is B. Question 1.7 again. 3 small identical spheres A, B, and C carry charges as shown in the diagram below. The distance between spheres A and B is x. So we have sphere A, sphere B, and sphere C. And the charge on sphere A is plus 4q. Charge on sphere B is minus q. Charge on sphere C is plus q. And the distance from A to B is x. For sphere B to experience a zero net electrostatic force, what must be the distance between spheres B and C? All right. Again, we will approach this similar to how we approach this 1.7 here. We will first argue that, now we're going to argue for distance. So we'll first argue that suppose the distance were the same. So that means if the distance from A to B is x and from B to C is x, then since sphere A is 4 times the charge on sphere C, and that the force is directly proportional to the magnitude of the charges, we would expect that the force that sphere A exerts on sphere B is 4 times larger than the force that sphere C exerts on sphere B if they were at the same distance. So since they are not, then we must position sphere C to compensate so that it also to increase the force on of sphere C on B to be 4 times larger as well. So then the only way to do that is by placing sphere C to the distance here must be half x. So force is inversely proportional to the square of the distance. So then if this is half x, then 1 over 2 squared would increase the force to 4. So then the correct answer here is B. All right. And then 1.10 diagram represents 3 energy levels, X, Y, and Z, in a certain atom. Energy difference between levels Y and Z is twice the energy difference between levels X, Y, and Y. All right. So probably it's wise to indicate this on this diagram, this information, that the energy difference between Y and Z is twice the energy difference between X and Y. So you would just let this be X, then this will be 2X, so that you know that from X to Z, if you analyze this diagram, then it's going to be 3X, meaning that the transition Q is 3 times, or the energy transition is going to be 3 times the energy transition of P. If the wavelength of a photon emitted as a result of transition of P from level X to Y is lambda, then the wavelength of the photon emitted during transition Q from level X to Z is, so here we will use the formula. E is equal to hc over lambda. Energy is inversely proportional to lambda, and from the diagram, from this information, we note that the energy Q, energy from transition Q is 3 times energy transition from P. So if this is lambda, then in order for this energy to be 3 times as much, how do you change lambda? So you change lambda inverse proportional. So lambda must be changed. Lambda must be third of the original of this, of this lambda P here. So the lambda on transition Q is going to be the third of the lambda on transition P, so that the energy from X to Y is 3 times the energy from, no, the energy from X to Z is 3 times the energy from X to Y. So the correct option there is D. All right, that's it. Thank you for listening, and if you're unsure, please let me know in the comments, but I suggest that please go through the proportionality videos. They are very helpful in order to respond to these questions with confidence. You can also have options of calculations, so everything is there. But please let me know if you need further clarity. Please let me know in the comments. Thank you.